Production LLMs can look healthy while quietly getting worse. In this section, we'll treat output quality as an operational signal, detecting drift from prompts, models, retrieval, and users, then closing the loop with metrics, evaluations, and human review. So far, we've made the platform scalable, resilient, and observable. Now the question is, are the answers still good after deployment? Quality monitoring addresses that question by checking drift, safety, and business fit before problems quietly reach users. In traditional software, uptime is a strong health signal. If the service responds quickly, returns few errors, and has enough capacity, we usually call it healthy. LM systems break that assumption. A request can return HTTP 200 and still be wrong, unsafe, off-brand, or unusable. The failure may sound fluent, which means dashboards focused only on latency and error rate will miss it. Production monitoring has to combine infrastructure health with behavior and output quality. Factuality, schema compliance, safety, usefulness, and whether the answer completes the business task. Production quality is a portfolio of signals, not a single score. Format signals tell you whether the system produced something usable. Valid JSON, required fields, and correct tool calls. Behavior signals check whether it followed instructions, matched the expected tone, and stayed within safety boundaries. Accuracy signals ask whether the answer is grounded, consistent, and free from obvious hallucination. Business signals connect output to outcomes, such as user feedback, corrections, completion, or conversion. The key mental model is coverage. Each signal catches a different failure mode, and together they create a production-grade view of quality. A response can sound reasonable and still be unusable. If an API expects structured JSON, the first question is simple: can we parse it? Next, validate the contract. Required fields, allowed enum values, correct tool name, and valid tool call arguments. Keep these failures separate from refusals, safety blocks, and application errors, because each one has a different fix. Then slice schema validity by prompt version, model version, root, tenant, and use case. A sudden drop often points directly to the change that broke downstream automation. Refusal rate is not a simple lower is better metric. A healthy system balances two failure modes. Over-refusal blocks legitimate users, hurting helpfulness and trust. Under-refusal allows unsafe or prohibited content, creating policy and business risk. Track refusals by request category, customer segment, model route, prompt version, and safety policy version, because averages can hide the real problem. Use automated safety classifiers for broad coverage, and add human review for ambiguous or high-risk cases. The goal is calibrated behavior. Answer when safe, refuse when necessary, and escalate when uncertainty is high. Hallucination monitoring is less about proving absolute truth and more about checking whether each answer is grounded in available evidence. Compare generated claims with retrieved documents, knowledge base passages, or structured records. Measure signals like citation coverage, unsupported claim rate, contradictions with sources, and overlap between the answer and retrieved context. The evaluator might use entailment models, LLM review, or deterministic rules depending on risk and cost. Most importantly, separate retrieval failures from generation failures. If the right evidence never arrived, fix retrieval. If it arrived but was ignored, fix generation. Quality measurement should continue after the model responds. In a support draft workflow, the model suggests a reply, the agent edits it, and the customer outcome shows whether it worked. Capture direct feedback, such as ratings, reason codes, and escalation flags. Compare the draft with the approved final version to calculate edit distance and acceptance rate. Also watch the workflow itself: completion time, retries, abandonment, and task success. Later corrections from people or systems are valuable too. These downstream signals reveal real usefulness, not just surface-level output quality. Golden sets turn production risk into repeatable checks. Start with examples that matter: high-value tasks, risky requests, frequent patterns, and issues that have failed before. For each case, label what good looks like: the expected answer, acceptable variation, when to refuse, and how it will be judged. Run these cases automatically whenever you change a prompt, model, retrieval index, or routing policy. That way, failures become review items, not surprises. Keep the set alive by adding incidents, escalations, and human-labeled examples as the system evolves. Every production change needs the same regression discipline, whether it touches a prompt, model, retrieval index, embedding model, or routing rule. Treat the changed artifact as a candidate version, then compare it with the current production baseline using golden sets, pass-fail gates, and score deltas. Segmentation is the critical step. Averages can hide damage, so break results down by task, language, customer tier, safety category, and route. If critical cases fail, or quality drops beyond agreed thresholds, the pipeline stops before canary or deployment. Input drift is the gap between what your system was tuned for and what users ask for today. It can show up as new languages, longer prompts, different document types, higher token volume, or more images and files. The model may be unchanged, but quality, cost, and safety risk can still shift. Embedding changes are useful because they reveal semantic movement, not just keyword changes. Segment the signal by tenant, region, cohort, traffic source, and workflow. A global average can hide a fast-moving problem in one customer group, such as seasonal questions, policy concerns, or an emerging incident. Output drift is about how answers change, even when users ask nearly the same thing. A model may become more verbose, change tone, drop a required format, cite sources differently, or start refusing requests it used to answer safely. These shifts are not always wrong, but they are signals to investigate. Track response features like length, sentiment, reading level, structure, grounding, citations, and safety behavior by prompt version, model version, route, and retrieval source. Then compare embeddings and evaluator scores against known good baselines to spot meaningful movement early. Drift detection starts by comparing today's traffic with a trusted baseline. Use metrics like KL divergence, Jensen-Shannon distance, PSI, or embedding centroid shift depending on the signal. Compare scores over rolling windows, so temporary noise does not look like a real change. Segment results by route, tenant, prompt version, model version, and traffic class, because aggregate averages hide localized failures. Finally, set tiered thresholds. Observe small movement, investigate sustained warning levels, mitigate clear degradation, and rollback when risk crosses a critical boundary. This keeps alerts actionable instead of noisy. Automated metrics are the first filter, but they cannot judge every nuance. Production samples should flow into human review in two ways: routine sampling for ongoing quality, and targeted audits when risk, drift, or incidents appear. Reviewers should match the domain, especially for legal, medical, safety, or enterprise policy decisions. Their labels and findings should not sit in a spreadsheet. Feed them back into golden datasets: evaluator calibration, prompt changes, routing rules, and fine-tuning data. Customer escalations and support tickets are especially valuable because they reveal failures your tests did not anticipate. Quality monitoring and drift detection turn observability into control. Track signals like validity, refusals, hallucination risk, feedback, edits, and task success. Use golden sets and regression gates before changes ship. Watch input and output distributions for drift, then route alerts into automated evaluation and human review. Next, we connect these reliability outcomes to cost attribution and capstone architecture.